Hello, let us start chapter 3 module 5. In this chapter basically we have discussed several types of separation properties. For example, Hausdorff property. What Hausdorff property says? Hausdorff property says that for any two distinct points there exist disjoint open sets containing these 2 points. For example, regularity property. Regularity property says that if we take a point and a closed set, point is outside the closed set, then there exist disjoint open sets containing the point and the closed sets. We have also studied normality property. What normality property says? It says that if there exist two disjoint closed sets, then there exist disjoint open sets containing the closed sets. In addition to that, we have another separation properties for completely regular spaces. This says that if there exists a point and a closed set not containing the point, then there exists a continuous function which map the point to 0 and the closed set to 1. In fact, completely regularity property comes from Eurytion's lemma. Eurytion's lemma says that a space is normal if and only if any two disjoint closed set can be separated by a continuous function. That is, a space is normal if and only if given any two disjoint closed set there exists a continuous function which maps one closed set to 0 and another closed set to 1. So, this type of property we have studied in this chapter, but in this module we shall discuss some extension property of continuous functions, which is called T's extension theorem. In fact, this follows from Eurytion's lemma. So, this is not a separation property, but since this directly follows from Eurytion's lemma, we are including this T's extension property in this module. So, let us go to slide presentation. As we have discussed in this module, we shall discuss that how continuous function can be extended from a subset to the whole topological space. This does not hold everywhere. For example, if we consider x as the closed unit interval and let us consider a subset of x A is equal to 0, 1 open interval. Now, let us consider the function f x is equal to 1 by x, then f is a continuous function from A to R, but it is not possible to extend f all over the unit interval 0, 1. Our T's extension theorem says that if x is a normal space and k is a closed subset of x, then any continuous function from the closed set to R can be extended to the whole space. This holds for normal spaces. We also show that if in some spaces T's extension theorem holds, then that space must follow the Eurytion's lemma. Let us start with the T's extension theorem formally. So, let us start by stating T's extension theorem formally. Let X be a normal space and C be a closed subspace of X, then any continuous mapping from C into R may be extended to a continuous mapping over X. Just in the previous example, we have shown that example of a normal space and a subspace of the normal space, that is closed unit interval 0 1 is a normal space and the open interval 0 1 is a subspace of closed interval 0 1. But open interval 0 1 is not a closed subspace and we were unable to extend the continuous function f x is equal to 1 by x defined on open interval 0 1 all over closed interval 0 1. We can guarantee the extension in case of closed sets. Now, coming to the proof of this theorem, the basic idea of the proof is approximation. We will make a sequence of continuous functions and then we will take their sum such that the sum will be ultimately equal to f. So, let us come into the proof. Let X be the given normal space and C be a closed subset, and let f from C to R be a continuous map. Let us first consider the case where f is bounded. We shall handle the general case separately. Since first we have considered f is bounded, that means there exists some positive number m such that mod of f x less or equal to m for all x belongs to C. Now, let us consider the following two sets. A1 is equal to all x belongs to C such that f x greater or equal to m by 3 and B1 is equal to all x belongs to C such that f x greater or equal to minus m by 3. Then A1 and B1 are obviously disjoint because the set A1, every point of the set A1 is mapped under f greater or equal to m by 3. Now, both A1 and B1 are closed subsets of C, but C is closed in X and therefore, A1 and B1 must be closed in X. By Eurytion's lemma, therefore, we can find a continuous mapping G1 from X to the closed interval minus m by 3 to m by 3, which takes the value m by 3 on A1 and minus m by 3 on B1, and G1 takes the values in the open interval minus m by 3 to m by 3 on X minus A1 union B1. That means, we have a continuous function G1 from x1 to the closed interval minus m by 3 to m by 3 such that G1 maps the set A1 to m by 3 and maps the set B1 to plus m by 3 and G1 maps the rest part of X in between minus m by 3 to m by 3. Now, we can easily observe that difference of f x minus G1 x is less or equal to 2 m by 3 on C. Now, we shall handle with the function f(x) minus g1x, and let A2 consist of those points of C for which modulus of f(x) minus g1x greater or equal to 2m by 9, and B2 consists of those points for which modulus of f(x) minus g1x less or equal to minus 2m by 9. Again, we can apply Eurytion's lemma, and by applying Eurytion's lemma second time, we can find a continuous function g2 from capital X to the closed interval minus 2m by 9 to 2m by 9, which maps the set A2 to the value 2m by 9 and maps the set B2 to the value minus 2m by 9. Also, G2 maps rest of the part of x2 in between minus 2m by 9 to 2m by 9. Now, if we compute f(x) minus g1x minus g2x, we can see that modulus of f(x) minus g1x minus g2x less or equal to 4m by 9 on C. We can write it in this way: modulus of f(x) minus g1x minus g2x less or equal to 2 square m by 3 square on C. Now, let us repeat the process. Now, repeating the process n times, we get at n stage a continuous function gn from x to the closed interval from minus of 2 to the power n minus 1 into m by 3 to the power n, comma 2 to the power n minus 1 into m by 9, and also Gn satisfy that f(x) minus g1x minus g2x up to minus Gnx less or equal to 2 to the power n m by 3 to the power n on C, and modulus of Gnx strictly less than 2 to the power n minus 1 into m by 3 to the power n on x minus C. So, by the process of induction, we get a sequence Gn of continuous function such that at each nth stage Gn satisfies the following properties. Next, we define Gx as the sum of Gnx for all x in X. Now, to be well defined, we have to show that this sum converges, but this follows from the comparison theorem of calculus, because we know that the geometric series 1/3 summation 2 by 3 whole to the power n minus 1, n is equal to 1 to infinity, this converges. So, from this we say that Gx is well defined. Now, to show that G is continuous, we must show that the sequence of partial sums Sn of the sequence Gn converges uniformly to G. Since we know that sequence of a uniformly convergent sequence of continuous functions is continuous. So, if we can prove that the sequence of partial sums Sn converges to G uniformly, then we will be able to say that G is continuous. Now, we show that Gx is equal to Fx for x belongs to C. Gx is by definition the limit of the infinite sequence Snx of partial sums, since modulus of Fx minus summation of Gix I is equal to 1 to n is equal to Fx minus Snx, which is less or equal to 2 by 3 whole to the power n for all x in C. It follows that Snx converges to Fx for all x belongs to C, but we already know that Snx converges to Gx for all x belongs to C. Therefore, we have that Fx is equal to Gx for all x belongs to C, that is F and G agree on C. That means G is an extension over x of F. We note for use in the unbounded case below that modulus of Gx is bounded by M, because modulus of Gx is equal to n is equal to 1 to infinity modulus of Gnx, which is less or equal to summation n is equal to 1 to infinity m into 2 to the power n minus 1 by 3 to the power n, which is equal to m, and modulus of Gx is strictly less than m on x minus c. This follows from the previous equation B. So, what we have proved till now? We have proved till now that if f is a bounded continuous function on a closed subset of x, then f has a continuous extension. Now, we like to prove that this holds for arbitrary continuous function. For that, let f be arbitrary, that is f in this case let f be not bounded. Now, we can choose a homeomorphism H from the real line to the interval minus 1 to 1. Of course, that interval will be open interval. Now, if we consider the composite mapping H compose F, then the composite mapping H compose F is a bounded continuous function from C to minus 1 to 1 open interval. Now, by the above part of the theorem, H composition F must have a extension all over capital X, which is less than 1 and greater than minus 1 strictly. So, the composite mapping H inverse composition G is well defined, and by construction it extends F over capital X. This completes the proof of T's extension theorem. So, we have proved teased extension theorem. The proof basically consists of applying Eurytion's lemma successfully. Next, we shall prove some applications of teased extension theorem. Let us go to slide presentation. So, teased extension theorem says that if X is a normal space and C be a closed subspace of X, then any continuous functions from C to R can be extended all over X. So, this comes as a corollary of teased extension theorem, that any continuous function from C to any closed interval a b can also be extended all over X. The proofs follows the basic proof of our theorem. Though we have used Eurytion's lemma in the proof of teased extension theorem, but if a space satisfies teased extension theorem, then it satisfies Eurytion's lemma. That means, consider a space, we do not know whether it is normal or not, but we know that it satisfies the teased extension theorem. That means, any continuous function from a closed subset to R can be extended all over the X. Then that space satisfies Eurytion's lemma. That means, given any two disjoint closed set, there exists a continuous function f, say, such that f of one closed set is equal to 1 and f maps another closed set to 0. To prove this, let us consider two disjoint closed sets A and B in a space which satisfies teased extension theorem. Now, we can consider one continuous function, say f1, which maps A to 0, and let us consider another continuous function f2 which maps B to 1. Then by pasting lemma, we have another continuous map f which is equal to f1 on A and which is equal to f2 on B. Then since the space satisfies Eurytion's lemma, then f can be extended all over capital X, and then the extended function must be equal to 1 on one closed set and must be equal to 0 on another closed set. So, it satisfies the Eurytion's lemma. Next, we shall discuss some properties which can be said as byproduct of teased extension theorem. Let us introduce the following definition, which called the universal extension property. A space Y is said to have universal extension property if for any given normal space X, any closed subset A of X and any continuous function from A to Y, there exists an extension of f to a continuous map from X to Y. We can easily prove that R to the power j has the universal extension property. To prove this, let us consider a normal space capital X and a closed subset A of X and a continuous function f from A to R to the power j. Then we have to show that f has an extension all over capital X. Now, for each I belongs to j, if we consider f I is equal to pi I composition F, then Fi is a mapping from A to R, and being composition of two continuous function is continuous, and hence it has an extension say Gi over capital X. Now, if we define G is equal to Gi where I belongs to J, then G is a continuous extension of F over capital X. Note that here G is continuous as R to the power J has product topology. Let us introduce another notion say which is called retract. Let X be a topological space. If capital Y is a subspace of Z, we say that Y is a retract of X if there exists a continuous function from X to Y such that R is identity map on Y, that is R Y is equal to Y for all Y belongs to capital Y. It is easy to observe that if X is a Hausdorff space, then any retract of capital X is closed. As an example of retract, we can take S1 in R2 minus origin. The mapping from R2 minus origin to S1 defined by R of X is equal to X by norm of X is a retraction. Another example, if Y is homeomorphic to a retract of R to the power J, then Y has the universal property. Next, we are going to define another notion called absolute retract. Let capital X be a normal space, then capital X is said to be an absolute retract if for any normal space Y and any closed subspace Y naught of Y homeomorphic to capital X, the space Y naught is a retract of Y. We end this section by the following proposition that if X has the universal property, then X is an absolute retract. To prove this, let capital Y be a normal space and Y naught be a closed subspace of capital Y which is homeomorphic to capital X. Let F from Y naught to capital X be the homeomorphism. Since capital X has the universal extension property, there exists a continuous mapping say G from capital Y to X of small f, then R is equal to F inverse composition G is our required retraction. In this module, we have basically discussed the proof of T's extension theorem, which says that in a normal space, any continuous function from a closed subspace to R can be extended all over capital X. We have also discussed some other extension properties. With this, we end this module. Let us pass to next module.